Hello everyone, thank you for joining today's webinar on Design and Optimization of PMSM for Wind Turbine. I am Sumit Singh, an electric motor expert at EMWorks. EMWorks is a leading provider of electromagnetic simulation software for electrical and electronic designs, from DC to millimeter wave frequencies. Our products are embedded in the most popular CAD platforms, namely SolidWorks and Inventor. They cover a wide range of applications ranging from electric motors, generators, transformers, and power electronics at the low frequency end of the spectrum to antennas and various wireless circuits and components at the high frequency end of the electromagnetic spectrum. Moving ahead, let us look at the agenda for the technical presentation. First, I'll talk a little bit about the machines that are used in the wind turbine sector. Then we will go through the different topologies of PMSM. Then we'll see what are the design challenges and how an EMWorks products can help and what are the solutions for your design. Then we will look at some of the analytical modeling and finally the results and discussions. And then later I'll conclude today's webinar. Well, as we know, with the rapid growth in the global energy needs, the wind turbine has emerged as a reliable solution, one of the reliable solutions to face the problem of climate and ecological changes. We have direct drive permanent magnet synchronous machines which is used in wind turbines and have received a significant attention, especially due to the elimination of gearbox noise and their low maintenance cost. PMSMs provide a high energy efficiency and a better magnet yield. In addition, the absence of circuit exciters reduces the maintenance cost of the generator's rotor and also minimizes its losses, which in turn helps to achieve a better thermal effectiveness and a higher performance. Various machines are used for energy conversions for wind turbine systems. The most famous wind turbine generators currently used in wind energy conversion are asynchronous generators such as squirrel cage induction machine, double fed asynchronous generator and permanent magnet synchronous generator. So the question comes here is, how should we choose a machine for our wind turbine conversion? So find the answer for that. Let's go through each different types of the generators. So the first we have squirrel cage induction generators. They operate at a fixed speed. They are standardized and have a low cost and less maintenance by using a simple electrical interface and eliminating the power electronics. They are usually used for high power wind turbines like above 100 kilowatt. The use of the gearbox for high speed affects the mass of the wind turbine, and also the energy capture is not optimal because the speed is not controllable and it has a range of variation is very limited. Next we have doubly fed induction generator. The doubly fed induction generator have the same operating principle as that of squirrel cage induction generator, that is having a one rotor. They are innovation comparing to squirrel cage induction generator working with variable speed. The design is complex due to the presence of brush ring assembly and the mechanical speed multiplier, but they require regular maintenance and their connections with the network needs power electronic interface too. And finally we have permanent magnet synchronous generator. They operate at a variable speed with reduced cost and volume. They can be used directly or via mechanical gearbox. The possibility of absence of the gearbox permit to avoid gearbox noise problem and also reduce maintenance costs. And we can also say that the use of permanent magnet provides a strong magnetic field in the air gap, and that is one of the key advantage for such type of generator. Also, the absence of the excitation circuit at the level of the rotor minimizes the losses by joule. The brush ring assembly is eliminated. The design is simple. And due to the large number of poles, we use polytronics interface. But the major drawbacks of this type of machine is the high cost of the permanent magnets. So based on the requirements and cost of the project and where you want to install your wind turbine, you can select either one of them, what kind of performance you're expecting out of it, and also the budget of the product. Moving ahead, now we will be focusing today's our presentation mainly on the permanent magnet synchronous generator, and we have various famous topologies. First, we can differentiate or classify these generators based on the nature of flux, and we have axial flux machines and radial flux machines. Radial flux generators, permanent magnet generators, are preferred for a wide range of velocity variation. They are slightly more efficient and require fewer active materials than compared to axial flux generators. Next, we can classify based on the nature of the rotor. We have internal rotor and external rotor. External rotor generators have the advantage of less iron volume in the stator, hence a decrease in overall weight compared to internal rotor generators is there, and they also decreases in overall weight compared to internal rotor generators. And finally, we can classify based on the nature of permanent magnets. It can be either surface mounted PM generator, it can be either inserted or inset, like completely buried permanent magnet, which helps in flux concentration. And the most popular design you can see is the V-shaped permanent magnets, which is one of the interior permanent magnet design. Surface permanent magnets offer better performance in terms of efficiency, mass, power factors. They have the simplest design, but for the buried PMs are difficult to insert and cause greater torque ripples than surface PMSM, but the flux concentration helps to improve the performance of overall generators, and we need to choose our design based on our requirement and the application. Moving ahead, so let us go through some of the challenges which we face while designing these motor. So there is a traditional method which is also called as analytical method, and of course it's not very reliable, and we need an expert designer to calculate those equations, and it takes a lengthy process, it's expensive and complex, and it has a limits on the variation of range of the design parameter. Of course, the equations cannot accommodate all the kind of variables that we need to consider while designing the motor. Also, these equations are very limited to the sketch of the machine, and or we can say the geometry of the machines, and such modeling presents 5% of the cost of the design activity and 75% of the cost overall the lifetime of the system. So moving ahead, and let us look at the solutions which are provided by the EMWorks. Basically, EMWorks has three different products. First, we have Motor Wizard tool. It is template based motor design software that allows user to accurately solve both electric and magnetic problems. It includes electrostatic, magnetostatic and transient solvers, which are equipped with integrated analytical and finite element based solvers. Second, we have the EMS 2D tool. It is a 2D electromagnetic simulation software that uses the finite element to solve magnetic, electric and transient problems. EMWorks 2D allows you to study the effect of the geometric or simulation parameter changes on the design. It also allows you to couple a transient magnetic study to mechanical motion and thermal. And finally, we have the third product. It's called as EMS 3D tool. It allows user to do both electric and magnetic simulations using the complete 3D geometry. EMS is a true multiphysics software that enables users to couple the magnetic and electric design to circuit, motion, thermal and structural analysis on the same model in a hassle-free integrated environment. So using these three products, we can simulate our motor application. So basically it's a one-stop solution for all your motor application needs. You can design your PMSM, machines using the analytical model first, and you can verify these in using this FEA based tool. You can couple the simulation with circuit components, and as you can see on the right hand side of the screen, we have a coupling analysis to rotational motion, thermal coupling, also coupling to circuit. You can also choose different types of analysis, that is magnetostatic, electrostatic, or AC magnetic or transient magnetic, and then here you can begin with the analysis. So let's go back to our today's webinar topic, and here is the model that we are considering for the wind turbine application, and we will optimize the number of rotor poles as you can see in the later slide. So we have a surface PMSM model with an internal rotor. We have a magnet which is neodymium, and we have used the stator core as a electric steel, and then we have a winding coppers. First, to begin with the analytical analysis, these are the terms which we will be using in the equations, that is slot width, the magnet width, the magnet thickness, slot depth, the axial length of the machine, the stator back iron core thickness, and the rotor core thickness. So these are the few parameters which should be obtained to get our desired specification or the results. So here are the equations which we will be using to compute our motor geometries or parameters. So first you can see here is the equation to calculate the bore radius, then along with that you can calculate the machine length, then it's very important to calculate the air gap thickness accurately because it determines your electromagnetic performance, and then we have a slot width. Similarly, we have different parameters such as the performance parameter, which is magnetic flux density, and back EMF, which we will verify using the FEA based tools. So once we have used these equations and calculated our motor geometry, here you can see some of the parameters. So we have specified that we need a motor for 1100 watt, and since it's a wind turbine application, we have set the RPM speed very low, which is around 382 RPM. We have considered a pole pair number of 6, and the stator yoke induction is at 1.4 Tesla, and we have also set the slot per pole per phase as 1, and we want our current density to be around 2.7 ampere per millimeter square. After using these parameters and with the help of analytical equations, we get the list of the geometric parameters, and on the right hand side you can see all the values, and also we have some electromagnetic parameters where our maximum flux linkage is around 0.34 Weber. We have a back EMF of 82.5 volt, and then we have a magnetic flux density in the air gap around 0.85 Tesla. Moving ahead, now we'll use our AIMWorks 2D solver to simulate our analytical design, which act as a reference PMSM, and we'll see how we get our result, how much error do we have between our AIMWorks 2D software, FEA based solution versus analytical, and then we'll try to optimize by varying the number of pole pairs. So here we have our reference machine. On the left hand side you can see it's a 2D geometry, and we have computed its magnetic flux density lines. As you can see, the peak is in the stator tooth, which is around 2.01 Tesla. Next we can also see its magnetic flux density plot, and the peak is around the average of the peak is around 0.8 Tesla. And next we have a magnetic flux linkage which is around 0.34 Weber, and we have also plotted its induced back EMF, and you can see it's more kind of a BLDC motor, and the back EMFs are very much in trapezoidal fashion, and we'll see how we can play with the pole number so that we can reduce our magnet pole arc so that we get more kind of sinusoidal back EMF. Well, its peak is around 60 volt, and then we have a cogging torque of our reference PMSM, which is very huge, and it's going from peak to peak is around 20 Newton meter. Now let us compare the results what we have done through analytical and the numerical value using the EMWorks tuning. So if we just compute some of our key parameters, that is, the first is magnetic flux density, and we can see we have an error of 3.3% between the analytical and FEA based solver. Then next we have the magnet flux linkage at no load condition, so we have 1.3% error. And then finally we have a back EMF voltage, and of course based on the material types and the core material we get error, and it's huge. So we need to now optimize using our FEA tool our geometry so that we get our desired results. So far what we have seen that our reference machine has a very high cogging torque, and to optimize the machine performance we are simply varying our pole pair numbers. We can vary a lot of parameters in the motor, and it's all a trade-off between what kind of parameter you are flexible with and what parameters you don't want to change and stick to the same. So for here in our case we have kept the geometry as a constant. We don't want to vary our outer diameter or the length of the machine, so our stator core is fixed. We'll be simply varying our pole pair numbers in the previous design, and also the magnet width will be changing accordingly to maintain the magnet volume almost the similar in all the cases. So what we do here is we use our P pole pair as a 6 as a reference design, and then we try to increase our pole pair from 6 to 8, then 10, and then 12. We keep our frequency as same, therefore our speed will be changing. Basically it will be decreasing as we increase the number of pole pair. We have kept the model length as same, and the magnet arc in the degree is varying because we are increasing the number of pole. So now each magnet will have, instead of 27 degree, will reduce to 13.5 degree in case of once we double the number of pole pairs. Next, here we see the magnetic flux density, and more or less it's the same. It's not varying with increasing the number of magnet poles because overall the magnet volumes remains the same. Therefore the saturation which is occurring in the stator cores will remain almost the same, and which is around 1.9 Tesla. And so yes, using this magnetic flux density it helps the designer to understand the flux path too, by referring its contour lines, and you can see the flux lines has increased as the number of pole has increased because we have more number of magnets, and which has a north and south pole alternatively arranged. We have the magnetic flux density and back EMF for a pole number of 8. So we can see the back EMF has improved. It's not anymore a type of trapezoidal, but still we need to look at the other types of result. So next, if we have a pole pair number of 10, it further improves, and of course we need to do FFT analysis to understand the harmonics component present in this waveform, but for now we can say it has improved a little bit better than compared to the previous pole pair as 8. And also we do see that magnetic flux linkage has a now more better sinusoidal shape, and that's a positive sign. And again, if we switch back to the pole pair of 12, we do see that flux linkage has improved, but our back EMF has again tending towards, and it has some kind of third harmonics component now introduced in the model. So we computed its FFT analysis for the induced back EMF for all the four different designs. As we can see, the THD is lowest for the pole pair of 10, and we also computed its cogging torque, and we can see for the pole pair it's ranging from 0.1 to -0.8, and its Then if we look at the pole cogging torque for the next model, it is reduced a lot, and we see that it's not going as high as 0.1 in this case, and it's reduced compared to the pole pair of 8 design. And let us also see for the third design, which was 12, and we do see that it's very high in case of pole pair 12. So of course there is you can parameterize the model and you can find the optimal design, but this was kind of a hit and trial by varying the different pole numbers, and we came up with the F50 analysis for the back EMF, and based on the torque we found that the performance was much better for pole pair equal to 10. So for the further analysis we'll just go with our optimized model as pole pair equal to 10. So what we did in this webinar is we computed the back EMF, and we found the optimal design is for pole equal to 10, and this is one of the variable which we have varied and checked the performance. There are other parameters also that need to be varied and optimized. This is just a part of the optimizations for the model. We have seen the cogging torque was lowest for the PMSM having a pole pair of 10, and we also see that the slot pole per phase has reduced because the winding configuration changes, and for the optimal machine it was 0.6, whereas for the reference machine which we started in the beginning was 1, and also the winding type has changed from distributed to concentrate. So these are the parameters which you can observe, you can optimize, and you can see how your reference machine get optimized just by increasing the number of pole pair, and how the cogging torque reduces. And it is one of the key parameter to reduce the cogging torque because it also affects the noise and vibration in the. To conclude our today's webinar, we saw the analytical model for the surface PMSM to get the feasible geometry, starting geometry for our solution, for our design, for our specification, and then we validated it using EMWorks 2D software, and later we optimized the reference machine to reduce the cogging torque ripple and also to improve its back EMF. And for the optimization we have used different number of pole configuration which in turn has affected our winding configuration and led to such type of performance. And here are the references which we have referred for our today's analysis. So thank you everyone for joining us today, and now the floor is open for a Q&A session. Thank you so much, and I request all the attendees to ask your doubts in using the chat box option, and we'll be very happy to answer all of them. Thank you so much. See you in the next webinar.